An Investigation of Various Masses and Drag Force by Gabby Braconecki, Sheridan Perry, and Taya Smith.
This is a brief overview of what we're going to go through. First, we need to define some terms. Drag force is the resistance to an object's motion as it moves through a fluid, and in this case that's air. The drag equation is force equals 1/2 the drag coefficient times the density times pi r squared times the velocity squared of an object. The terminal velocity is defined as the steady speed achieved by an object freely falling through a gas or liquid. That's achieved when the speed of a moving object becomes constant or when acceleration becomes zero. Thus, at terminal velocity, it's equal to F drag or F resistive or F gravity.
Within the system schema, we included the Earth, which provides force of gravity to the filters and air resistance. Our force diagram of the filter has arrows of gravity and resistance of equal magnitude. Our pi energy diagrams begin before the drop, showing majority of the energy being internal and a third gravity. Before terminal velocity was reached, kinetic energy took 2/3 of the diagram, and the rest was mostly gravity and internal energy. For this experiment, our hypothesis was air resistance will be directly related to the squared terminal velocity of the object. We believe this to be correct based on the drag equation that was provided to us. We were able to reject our null hypothesis since our data proved our initial prediction to be correct. Our experiment consisted of dropping coffee filters from a height of 216 centimeters. Each filter weighed 1.6 grams individually and had a diameter of 24.5 centimeters. We conducted 3 trials total consisting of 1 dropping 1 filter, 8 filters, and finally 16 filters.
We began a trial by placing a coffee filter at the top of the door, which was 216 centimeters above ground. We then began timing and recording as soon as the filters were let go. The filters were allowed to free fall, and the recordings were analyzed on tracker. We created position versus time and velocity versus time graphs, and then further analyzed these to create a terminal velocity versus F drag. The first trial had 1 coffee filter, and the position is moving up and down due to the coffee filter's fluttering. We then took a velocity versus acceleration graph and used a line of best fit to later figure out our terminal velocities.
In our second trial, we used 8 coffee filters, and the first graph shows the relationship between the position and time for the coffee filters as they were dropped from 2.16 meters. The second graph shows the relationship between the velocity and acceleration, and we also used a line of best fit, which gives our equation y equals negative 0.0519x minus 0.109. This equation will be used in the upcoming slides.
Here you can see the data for dropping 16 coffee filters on a position versus time graph and a velocity versus acceleration graph. You can see on the position graph that the added weight to the filters makes it drop a lot faster with less flutter compared to the position of the graph of the 1 filter.
Here we can see our data comparison, which shows the relationship between the mass, the number of filters, the terminal velocity, and the air resistance that's at terminal velocity. For 1 filter, our terminal velocity is about negative 1 meters per second, while our air resistance is at about 16 newtons. For our 8 filters, our terminal velocity is about negative 2 meters per second, while our air resistance is at 125 newtons. And our 16 coffee filters give a terminal velocity of about negative 6 meters per second, which is approximately 249 newtons.
Here we plotted the squared terminal velocity over force, and we found that as velocity squared increases, we can see that force increases as well, and you can clearly see a linear relationship. The r squared value just shows that our data is statistically significant.
Resistance occurred due to viscosity and the fluid molecules being pushed along with our object. Due to Newton's third law, the molecules exert a force back onto the object that's the direct opposite of the motion. This is our drag. Terminal velocity is achieved when the speed of the moving object is no longer increasing. This is also when acceleration is equal to 0. The force of air resistance is approximately proportional to the speed of the following object, because air resistance increases for the object that is accelerating, having been dropped from rest until terminal velocity. At terminal velocity, air resistance equals the magnitude and the weight of the following object. The total force of the object is 0, and the speed of the object has become constant.
Comparing our real-world versus simulation examples, our group realized if an object is given enough time while falling, it will reach terminal velocity eventually, and this can be seen with our base jumper example and also with our in-class example. And now we reach our conclusion. This helped us determine that the terminal velocity of an object increases as the mass of an object increases. There is a linear relationship between velocity squared and air resistance, or F drag. So due to that, we can say that velocity squared is directly related to F drag. And a few reasons for error in our lab is that 2.16 meters is not enough time for an object to reach terminal velocity depending on its mass. And we also had some tracking or human errors, which could lead to tracking the wrong particle and off-center points. Lastly, the heating and the cooling in the building might have affected the amount of time it took for our objects to reach terminal velocity.